All right, hello guys. I'm not sure if you guys can hear me. Can you guys let me know in the Zoom chat if you guys can hear me? Ooh. All right, perfect. I was gonna throw on my webcam, but I've already started recording this, and the recording program is using my webcam. So apparently, no webcam. But in the recording, I will have a webcam. So I guess I'm sorry about that. That was an oversight I didn't really anticipate. So hold on one second. I'm just going to share my screen as well. Perfect. So now you guys can see my screen, hopefully. Hoping so, at least. I'm going to take it as a yes. All right, guys. Welcome to Civi 398 seminar. Assuming that you guys are all online students. I invited the in-person students, but for now I'm going to assume that you guys are all online students. So this will be kind of our first interaction, which is nice. So welcome to Civi 398. I hope you guys are having fun so far. I know that there's been a lot of technical difficulties, which is unfortunate, but we're getting through it, and hopefully we'll get better as the semester progresses. Just really quick, because you guys are online students and I haven't really got your input too much thus far. How are you guys finding the course? Has it been fine so far? Is there anything I can do to make it easier for you guys, or general comments at all? All right. Some of you guys may be typing. I'll keep an eye on Zoom chat as we go on, so feel free to ask any questions if you guys will, or any questions that you guys want. I'm going to start the presentation, and I just want to talk about what these seminars are. Oh, it's been great so far. Oh, that's great to hear, guys. These courses, they're all about you. So if you guys are having a good time, then I'm having a good time. So if you guys start to say, you know what, Clayton, this can be improved by doing this, this, or this, just let me know and I'd be happy to accommodate. I know it's really hard taking a class online, so whatever you guys need, I'll be here to provide. All right, so let's talk about the idea of these seminars. So what happens, as we talked about a lot in the in-person lectures, and I've kind of touched upon it in the videos that I provided for you guys as well, is that we have weekly assignments. They're due every Friday at 5 o'clock with some exceptions. Usually the 2 midterm weeks, there's exceptions. And basically the seminars can be, or the assignments can be a little bit tough. A lot of this course can be very abstract to students, and they have a hard time with it. I myself did my undergrad here at U of A, and I've taken this class as a student, and I remember thinking, holy crap, I don't know what any of this means. So when it came to the assignments, it was basically just playing guess and check. I want to try and eliminate this because it's not very known, but a lot of the stuff we learn in this course is very, very applicable to civil engineering, mainly structural engineering. What I like to say is this course is simulation math, meaning that everything that we are focusing on in this course goes into simulation. And how can we simulate stresses, strains, forces, displacements, all those fun things. Unfortunately for us, before we can get into that simulation part, we have to go over some mathematical preliminaries. So that's been the goal this week up until today, and next week as well. So this week has been about just general mathematical preliminaries, and next week we're going to get into linear maps, which are basically just matrices. After that, we are going to get into the actual fun stuff, stresses, strains, etc. But now I'm kind of getting off topic. So these seminars are just to help you guys with the assignments. That's it. There's nothing due at the end of the seminars, anything like that. We're just going to go over the assignment questions. It gives you guys, as students, a chance to ask me any questions you guys have with the assignment, or basically just hopefully answer as many questions as I can. So when you guys are doing these assignments at 3 a.m., there should be no difficulty at all. At least that's the goal here. I know that third year wasn't a hard year because usually everything seems to flow very nicely in third year, but it's a busy year. I know a lot of you guys have very, very full schedules. So if I can try and eliminate all that guessing time that you guys have with these assignments, then of course I'll be happy. So we're going to go over assignment 1. There's been a couple of tweaks here. And it's nice because at this point right now, I've done the 2 in-person seminars. So I have a good idea of what students will ask. So I'm going to try and cover all the questions I got asked in the previous seminars, as well as answer your guys' questions here today. And again, this will be recorded. That's why my webcam's not working, because it's actually recording me right now. And from there, I'm going to upload it so that you guys can come back and watch this seminar whenever you guys want or at your leisure. Alrighty, so that's kind of my introduction. I know is a little bit long, but now we're going to actually jump into the fun. So this is Civi 398 seminar, and it's going to be focused around assignment 1. How do we solve assignment 1? So if we look at the first question, it talks about what we covered in last lecture, lecture number 2. So not what we covered today, what we covered in the last lecture. And I know, I guess you guys are at a little bit of a disadvantage because I'm still waiting for the AV techs to give me lecture 3, so you guys haven't seen it yet, but we'll talk about it today. So question 1 says, state if the following functions are injective, surjective, bijective, or none of the above. I always like to tell the in-person students that this is very important to us when it comes to simulation. Because what happens is, for simulation, we always want all of our maps to be bijective. Because if something is bijective, it means it's invertible. For instance, if I know my forces, I can figure out my displacements. But I can also work backwards and say, okay, if I know my displacements, I can figure out my forces. So this is why we learn it. We want to be able to identify a bijective map. But of course, there's other types of maps. So question 1 here has 3 different parts, and it's basically just 3 different linear maps, and it asks you guys, are they linear maps? So I guess they're not really linear maps, but they're maps, and we're asking if they're injective, surjective, bijective, or none of the above. It sounds pretty crazy, but it's not too bad. Good question from Romani. What does it mean to be invertible? Exactly. It means that we can take the inverse. So what's going to happen when we start dealing with these structures is all of our displacements will be a vector, and all of our forces will be a vector. And we use a matrix to go between the two. So what it means to be invertible is, yes, this matrix will have an inverse. And from this inverse, that allows us to switch between the two. That's a great question. I'm glad you brought that up. So if we look at these questions, how do we determine if something is injective, surjective, or bijective? Well, it's pretty simple. First, figure out if it's injective. Second, find if it's surjective. And if it is both injective and surjective, we would actually say that the function is bijective. So that's the goal here. We want to verify that our function is injective as well as surjective, and then that will allow us to conclude that it is bijective. If it's neither injective nor surjective, then we would say it's simply none of the above. Now, whenever you guys see one of these questions, whether it be on the assignment this week, the midterm, or the final, the key step to doing them is always plotting them as functions. When I give you guys these types of linear maps, they're going to be in the following form, where basically we have a function that goes from a set of numbers to another set of numbers, and then I give you guys the function. Those 2 letters, in this case it's the set of real numbers twice, those are going to be the key to these types of questions. The function is easy enough. If I were to give you guys f of x equals x, without even taking this course, you guys know exactly what that function's saying. It's those 2 letters that start to confuse students. So we're going to talk about them. The first one tells us the domain of the function. What this basically means is, where are we plotting our function over? If we look in this case and we're plotting it over the reals, the set of real numbers, then we're plotting our function from negative infinity all the way to positive infinity. I hope that makes sense to you guys. The tricks come in is when I can switch this up. So sometimes you guys will see, and I think this is on the assignment, where instead of the set of real numbers, I give you guys the positive set of real numbers. So if that was the case and I gave you this r plus, we are now plotting from 0 to infinity. One of the tricks here though is that we're not plotting the point 0. We're going from just over 0 to infinity. It's an open interval. I can switch it up and I can give you r minus, the negative set of real numbers. So this would include all of the negative real numbers. So that's the first key. You look at the first letter to determine how you're plotting this function. Once you have the plot, then we can go and determine if it's injective or if it's surjective. So if I were to go here and say, okay, well, an injective function is a function where only a single value of x returns a value of y over a specified domain. Now again, I like to try and relate this to reality. a lot of students get lost in the mathematics of this course and they more or less treat it as a continuation of Math 102. I didn't like Math 102, the linear algebra course, because to me it didn't really have a lot of meaning. I work better when I can see exactly what this means. So if we were to look at an injective function, what I'm basically checking is that each value of x has a specified output. What does this mean physically? Well, let's say that I'm putting a force on an object and I want to measure displacement. So I put 100 kilonewtons on my object. What I want, if it's an injective function, is for there to be one displacement associated with that force. If I have a linear map and I were to put 100 kilonewtons and then my linear map returns, well, it could be 10 millimeters, it could be 20 millimeters. Well, we know that that doesn't really make much sense. There should only be one value of displacement associated with the value of force. That's why we try and determine if a function is injective. Now, how do we do this? Well, it's actually pretty easy. We take our function, we plot it just like we talked about, and then we do what I call the horizontal line test. All we're going to do is we're going to draw a horizontal line and we verify that this horizontal line only intersects our function once. If we look here, we can see that our function is only intercepted once. So if I wanted an output of, let's say, y equals 2, there is only one value of x that will return that, which is x equals 2. And I can do that for anything. If I wanted a y value of negative 100, there's only going to be one value of x that returns that value. So since there's only that one value, we can say that this function is indeed injective. Now it's very easy to see this and say, okay, well, that makes sense. When would it not be injective? Well, let's look at an example where it wouldn't be. If I were to change my function now to the absolute value of x, my function is going to look like this when I plot it. If I were to do a horizontal line test in this particular case, we now see that we intersect our function twice. Once at x equals 2 and once at x equals negative 2. They both give me a value of 2. So since two values of x result in the exact same output, the y value, we would actually say that this one is not injective. So again, the easiest way, just draw a horizontal line, you guys will be good to go. Is there any question about injective functions? You guys pretty comfortable with that so far? I'm hoping so, at least. If you guys have any questions, all in the chat. All right, perfect, all good. Thank you for responding. So let's move on to surjective. So in my experience, injective, students have no problem. They know how to draw a horizontal line, easy peasy. It's surjective functions which start to confuse students the most. So a surjective function is when a function, or when there's a single value, or it's not a single value, when there's a value of x to return every value of y on the specified codomain. Now you're saying, Clayton, that's a lot of words. What are you talking about? Well, remember when I give you a function, it's going to look something like this. And we said that the first letter there represents the domain. It tells me how I'm plotting my function. But we have that second letter. The second letter is what we call our specified codomain. It's our range of outputs that we're interested in. So if I were to look at this second letter r, in order for this function to be surjective, I must have an output for every set of real numbers. In this case, if I'm looking at my y-axis, I have to be able to obtain every value on that y-axis. So if we look at y equals 2, for instance, we're good to go because there's a value of x that returns this value. So hopefully that makes sense to you guys. So my question for you guys is, would this function in general be surjective? What do you guys think? Would this function be surjective? Yes, all right, you guys got it. This would definitely be surjective. Because if I were to look at that y-axis, the set of real numbers, I can obtain every value. If I wanted y equals negative 100, well, there is an input that will give me that. So this is the same for negative 4, and I can do this for every number. So since we can do this, we can actually conclude that this function is indeed surjective. Now, if you remember in the previous slide when we looked at this particular function, we also said that it was injective. So since this function is injective and surjective, Therefore, we would actually say that this function is bijective or invertible. Again, that's what we want in this course, is to find these invertible maps. Now let's look at an example that is not surjective. So we'll go back to this example where we have f of x is equal to the absolute value of x. If we were to look at the specified codomain, the set of real numbers, what this means is that there must be an output for the entire set of real numbers. And this is a problem because if we look at this function, it doesn't have any way for us to output negative numbers. Since we take the absolute value, there is no way we can get a negative number from this function. And since we can't do that, we would actually say that this is not surjective. So hopefully that makes sense. There is no value of x, for instance, that can return me a value of -4. And this, again, is important to us because we need to have that output for us. If we think about force and displacement again, let's say that I have a function that is able to return a displacement of 2 millimeters and a displacement of 4 millimeters. If that map cannot return a displacement of 3 millimeters, then something is wrong. We have to be able to cover the entire spectrum and not just parts of it. So this is why surjective functions are of interest to us. So we would say that this is not surjective. Now the key with surjective functions, and this is what's going to get you guys in exams, midterms, anything like that, is me changing that specified codomain. If I were to take that specified codomain, which is right now the set of real numbers, and change it to the positive set of real numbers, this function would then be surjective. Because if we look at this function, it is able to return me the complete positive set of real numbers. So I'm hoping that makes sense to you guys. So all you guys are going to do in question 1 is plot out your functions based on the domain, check if it's injective, and then look at the codomain and determine if it's surjective. So how are you guys feeling about question number 1? Because that's basically it for question number 1. Pretty good? Not too bad? I'm hoping so, at least. While you guys type, I'm going to show you guys one other thing really quick. So the only real trick, oh, hold on a second. So if the codomain was R+, that neglects the negative region and 0. Correct. That is exactly correct, Romani. Perfect. So it does neglect the negative region and 0. And that's actually why I wanted to show you guys this. Because if we look at B, question B, we have R+, but then we have a U and 0. So what this U and 0 means, it means union with 0. So in this particular case, our codomain would be all the positive real numbers and 0. So in this particular case, when I have that union 0, you have to include 0 as well. If that union 0 was not there, then we would neglect it. So I just want to touch upon that because we didn't really cover it in the lectures, and I'm sure some of you guys have never seen that before. So hopefully you guys are good to go now with question number 1. Question 1C is not surjective. That's a good question. Question 1C is not surjective. Why do you guys think that is? If we were to look at question 1C, in order for it to be surjective, it says that it has to be the entire set of real numbers, right? If we look at that specified codomain, we have to have an output of, let's say, 1.5. Now, if I'm plotting this function and my only inputs are integers, which is z, could I ever achieve a value of 1.5? Well, the answer is no. So this is why before we look at surjective, we have to plot the function. Typically, we plot the function as a set of real numbers, which is a continuous line. So a and b is going to look like a continuous line. But if we look at part C, we're not plotting a continuous line anymore. We're plotting only integer values. So it's actually going to just be a bunch of dots. And in between those dots, that's where we start losing our surjectivity. Because in between those dots, there's a whole set of y values that's unaccounted for. Does that make sense? Makes sense. Perfect. So again, the first thing you guys want to do in order to avoid this problem, plot out our functions. All right, perfect. Actually, I'll just skip ahead using this. Perfect. So question number 2. And this is all about proving stuff. And I'll be honest, I said this to everyone in person, and I'm going to really clarify it to you guys too. Whenever students see the word proof, they get scared. I don't blame you. I'm the same way. Proving things sucks. No one wants to prove anything. Here's the good news. This is one of very, very limited amounts of questions I will ever ask you guys to prove something. It's only because we're in the mathematical preliminary stage right now. Once we start getting into stresses, strains, all that fun stuff, you'll never be asked to prove anything. So don't worry about this. This is one of those very, very rare questions. Now, the first question I would always get asked if it was the in-person seminar is, okay, we're letting y equal alpha x, where x is a vector and alpha is any scalar. And students have no problem with that notation. But then they look at the very end and they say, well, that's equal to the span of x. And then they have a meltdown. Clayton, we didn't cover the span of x. What the hell does that mean? Well, you guys don't have to worry about it. The span of x is a very specific notation when we're covering a set of vectors relating to the x-axis. I put it there just to keep correct notation, but for the purposes of this question, you guys can just pretend it doesn't even exist. Okay? So it's just there for notation purposes. It doesn't mean anything and it doesn't add anything to our question. You guys can just pretend that span of x completely gone. All right? So don't worry about that. Now, if we were to look at this question, it wants two things. It wants us to prove that y is a subspace of R3, and it wants us to determine two basis sets for that particular subspace. All right, so it looks bad because it's a proof question, but again, I promise you guys it isn't that bad. So when we're proving subspaces, we have two main checks. All right, two main checks. You guys do these, you're good to go for this class. The first one is that it is closed under addition. That's going to be the first one, which basically means if I have a vector u and a vector v that are in that subspace, or in that vector space, then the resultant u and v, u plus v, must also be in that vector space. So that's the first check we're going to do. The second one is closed under scalar multiplication. If k is a scalar and u is a vector in the vector space, then k times u must also be in that vector space. So again, this is one of those very few questions I will ask you guys to prove it. Now, luckily for us, I'm going to do an example here that is even harder than the one you guys have in your assignment. So your assignment is simply just alpha x. It doesn't have that plus beta y. This adding the plus beta y, it makes it a little bit harder, but it's actually not too bad. So what you're going to do when you guys want to prove a subspace is you guys want to create vectors in that subspace to try and show what's going on. So if we were to look here, our vector is basically alpha x plus beta y. That's going to be the key here. So what we're going to do is we're going to create two vectors in the space. And how do we do that? Well, we look at what these vector properties are. Again, it's going to be alpha x plus beta y. So from this, I can create two arbitrary vectors. I'm going to have z1, which is alpha 1 times x plus beta 1 times y. And I'm going to have z2, which is alpha 2 times x plus beta 2 times y. So if we look at this question, when we define x and y, they're set vectors. They don't change. They're always going to be 1, 0, 0 and 0, 1, 0. So because of that, I don't put any sort of subscripts on the x and y vectors. They're always going to be the same. It's only alpha and beta that can change and can be anything we want. And because of that, I put subscripts on. So I got alpha 1 and alpha 2 because alpha, again, can be any real number. So what we're going to do is we're going to take these two vectors, and to show that it is closed under addition, we're going to add them together. So I'm going to take vector z1, and I'm going to take vector z2, and simply just add them together. So in its most basic form, this is what it's going to look like. It's going to be alpha 1 times x plus beta 1 times y, plus alpha 2 times x plus beta 2 times y. But we can actually simplify this, because if we look, we have alpha 1 times x, and we have alpha 2 times x. So we can actually rewrite this as alpha 1 plus alpha 2 times x, plus beta 1 plus beta 2 times y. Now this is important. This is the key here. We want to simplify it so that it has the exact same form as what is specified in our vector space. If we look at our vector space at the very top in that red box, it says we have a vector in the form alpha x plus beta y. And if we will look at z at the very bottom, it's going to be some coefficient times x plus some coefficient times y. They're the exact same now. So all we need to do now is look at the coefficients in front of x and y and make sure that they satisfy all of the requirements. So we're going to verify those components. Again, we had alpha 1 plus alpha 2 times x, and then we had plus beta 1 plus beta 2 times y. And if we were to look at these components, these are going to be the components that are listed above. So all we need to do is make sure that these components satisfy the conditions. Namely, alpha and beta have to be real numbers, or if we were to look at our vector z, we're basically just saying that these two coefficients in front of x and y, they have to be real numbers. So here's a question for you guys in the chat. If alpha 1 is a real number and alpha 2 is also a real number, then will alpha 1 plus alpha 2 be a real number? What do you guys think? If alpha 1 is real and alpha 2 is real, will the results of adding them be real? Yes, you guys are completely correct. So therefore, this coefficient in front of x, it satisfies our requirement because the addition of those two scalars is also going to be a real number. And I can do the same thing over with beta. If beta 1 is a real number and beta 2 is a real number, then the addition of them together must also be a real number. So what I would say, all right, alpha 1 plus alpha 2 is a real number, and beta 1 plus beta 2 is a real number. Therefore, z can be a subspace of z. And we can say that z is closed under vector addition, or z is an element to z. So that's going to be vector addition. When you guys do your own question, it's going to be the exact same process. In order to prove that it's closed under addition, you just create the two vectors, you rearrange them so that they have the same form as the question above, and then you just verify all the restrictions. In this case, my restrictions were alpha and beta have to be real numbers. If I looked at my equation, my two coefficients were indeed real numbers, no matter what happens. Then we move on to closed under scalar multiplication. The process is going to be exactly the same. We're going to multiply a vector by a scalar and then verify the components. So what I can do is I can create a vector z, which is k multiplied by our vector, so alpha x plus beta y. And we know that due to our distributive properties, I can write this as k times alpha times x plus k times beta times y. And again, we look at this and say, okay, my coefficient in front of x is k times alpha. Now, if k is a real number and alpha is a real number, then the multiplication of them together will also be a real number. Same with k and beta. So I can say, okay, well, since k alpha is a real number and k beta is a real number, we're good to go yet again. And this is closed under scalar multiplication. From there, I would say, okay, since z is closed under addition and closed under scalar multiplication, z is a subspace. So what do you guys think? How was that? Was it as scary as you guys thought it would be? Pretty easy, I'm hoping. It's one of those very few questions I will ever ask you guys to prove something. So I'm hoping it wasn't too bad for you guys. If you guys have any questions, just throw it in the chats. I'm constantly looking at it, even though you guys can't see my face. All right. So we are going to move on while you guys are typing and just answer this question now. What does z represent? All right, I want you guys to think about that. What does z represent? And while you guys are thinking about it, let's write z as a vector. We know that z is equal to alpha x plus beta y. Now, one thing that we were given was that x is 1, 0, 0, and y is 0, 1, 0. Alpha, beta, they can be any real number. So if I were to expand this out, I get that z is the vector alpha, beta, 0. So what do you guys think that this vector represents? What do you guys think? If I had a vector alpha, beta, 0, and alpha and beta could be anything, what do you guys think? What does this physically represent? Getting a little bit tricky. What this vector actually represents, yeah, it's the plane formed by the vectors 1, 0, 0 and 0, 1, 0. And as a lot of you guys know, those two vectors represent basically, or most of the time for you guys, the xy plane. So if alpha and beta can be any real number, then that vector is every vector in a 2D plane. So nice job. That's exactly what it is. And why am I telling you guys this? Well, remember that for these type of questions, or sorry, for part B of this question, we have to list some basis vectors that can form this vector. So if we were to say, okay, what basis vectors can we use to represent this plane? Well, two possible ones that are very simple are E1 is 1, 0, 0, and E2 is 0, 1, 0. If I have these two basis vectors, then I can express that vector alpha, beta, 0 as a linear combination of these two. If I wanted a different set, well, I can say, okay, well, instead of 1, 0, 0, I can go negative 1, 0, 0. Instead of 0, 1, 0, I can go 0, negative 1, 0. So basis sets, and if it ever asks you to list some basis sets, the best way is just to go with old reliable here. That's what I call these ones. 1, 0, 0, 0, 1, 0, and 0, 0, 1. With those three, we can represent everything in 3 dimensions. Now you guys say, Clayton, what about 4 dimensions? Well, we don't deal with 4 dimensions in this course, so you don't have to worry about it. So hopefully that makes sense. So is there any questions concerning question number 2? Because that's it for question number 2. I hope it's pretty straightforward for you guys. All right, I'll move on. Some of you guys may be typing, but that's okay. I'll answer it if anything pops up. We're going to go to question number 3. Now, this is where things get a little bit wonky because last year this was the original question number 3, where we basically had 2 vectors, x and y, where y was unknown. So it has 3 unknown components, y1, y2, and y3. And then I gave you 3 conditions. So basically I gave you 3 equations, 3 unknowns, and I asked you guys to solve for y1, y2, y3. Unfortunately, since these questions are randomized, or like with random numbers, there were some situations where there was not a possible solution. So what we did this year is we split it up. So this one has it kind of in the old format, but this year it's much simpler, where basically you always have 1 equation with 1 unknown, and you solve for that unknown, with the exception being part C. And we're going to talk about part C, so don't worry about that too much. So basically, this is what we covered in today's class, and hopefully I'll have that video up by the end of the night. I'm still waiting on that AV Tech, unfortunately, so I will keep you guys updated as that goes. But it says consider the vectors x, which is 2, 4, and 3, so we're going to be given one of the vectors, and a second vector y, which is y1, y2, y3. Now in some of the parts of the question, I think part A and B, it does give you 2 of the components of y. And it says it wants us to determine the components of y such that, and it gives basically a bunch of different conditions. So first one is the Euclidean norm of vector y is the square root of 41. We talked about this in today's lecture. Whenever you guys see Euclidean norm, it sounds really scary because it's a big word, Euclidean, and let's be honest, no one knows what the hell that means. And then it says norm. Although you guys may have not seen it in this particular notation, Euclidean norm of a vector is the exact same as the magnitude of a vector, which you guys did a lot in Eng 130. So this is something you guys have actually seen before. Same thing with part C, which is orthogonal projections. Projections are another thing we did in Eng 130. So I'm just going to go through these and we're going to just talk about each one. So Euclidean norm, we talked about today. It has a nice formula for 3 dimensions, where all we're doing is we're taking the components, y1, y2, y3, we're going to square them, add them together, and then square root it. So what I believe for question 1, or part A of this assignment, it gives you y1 and y2. So the only unknown in this equation is going to be y3, 1 equation, 1 unknown. You guys can solve for y3. So again, Euclidean norm sounds scary, but you guys have most likely seen it before in Eng 130 when you dealt with the magnitude of vectors. The second one is Euclidean distance. Now, this one's a little bit worse, but it follows almost the identical formula to the Euclidean norm. And what this physically represents is the distance between 2 vectors. And this is calculated as follows, where all we're doing is the same thing from above, but instead of going x1 squared, x2 squared, x3 squared, we go x1 minus y1 squared, x2 minus y2 squared, etc. So I believe that this is similar to question 1, where we know x, the whole vector. So x1, x2, x3 Those are good to go. We know what those are. And I believe we're given two components of y. y1 and y2, they're provided. So again, we have one equation and one unknown, being y3. You guys can solve for y3. It's number 3 that has given students some problems. The projection of y onto x. Now it's written in backwards notation, and I sent you guys an email about that a little bit later on. This is actually the scalar projection of y onto x. The formula you guys see in the notes will produce a vector. This formula right here produces a scalar. It's basically the magnitude of that vector. Now, the only thing that's going to cause students problems with this particular one is instead of giving you guys parts of y, so for instance y1 and y2, we don't give you anything. And I've gotten so many messages about this. What I did is I said y is equal to y1, y2, y3, so we have 3 unknowns, but we only have one equation. Now if I have one equation but 3 unknowns, how many solutions are there? What do you guys think? How many solutions are there if I have 3 unknowns but only a single equation? Infinite, exactly. So what we did is, again, all these questions that we put onto E-class, and this is why there can be so many bugs in them, is they're all parametric. They don't have one set answer. So all you guys have to do is provide one of those infinite solutions. So what I like to do, because you guys will see this again, the idea of picking one of the many solutions is just take 2 of the variables, y1 and y2, and set them equal to 0. Then solve for y3. Or if you guys want, you guys can set y1 and y3 equals 0, solve for y2. Again, you're just providing one of those infinite solutions. If it's a valid solution, you guys will get full marks. Does that make sense to you guys, hopefully? I got a lot of questions on this one right here. It's kind of funny to watch. All right, I'm going to assume you guys are good. Again, if you guys have questions, type it on the chat. I know you guys can't see me, but I'm just constantly watching chat for your guys' response. So that's going to be question 3. It should be very simple. It's what we covered today, which I will try and upload by the end of the night, but it's basically just a review of all the different equations we learned in Eng 130, with one exception, being question 5. So that's question 3, and then we go on to question 4. So question 4 is something that we covered in Tuesday's lecture, the idea of linear independence or dependence. So it says consider the vectors x, which is 1, -2, and y, which is -3, 4. It says prove that the vectors are linearly independent. So it's not asking if it's linearly independent or dependent. We already are given that it is independent and we just need to prove it. But that's very simple. After that, it says find the unique expansion of z in the basis set b equals x, y. What does this mean? Well, it means that I am using x and y, defined above, as my coordinate system. And if I'm using that as my coordinate system, that means that I can write z as a linear combination of x and y. It's going to be very simple. We're going to go through it and you guys are going to be very happy. Now the last one is actually kind of a fun question because there's a lot of different answers, just like question 3 part C, but there's kind of a cheese answer. If you guys like to speedrun video games, you guys will love this one right here. It says propose a new vector y such that the vectors x and y are linearly dependent. Now off the top of your guys' head, do you guys know a vector that will automatically make this linearly dependent? What do you guys think? Is there a vector that will automatically satisfy the idea of linear dependence? The 0 vector. So I got it as a direct message. Oh, but you guys are all catching on. The 0 vector. So it's one of those kind of fun trick questions where you guys don't even have to do any work for part C. We know that if we have a vector, or if our basis set contains the 0 vector, it's linearly dependent. All right, so hopefully that makes sense to you guys. But what about questions 1 and 2? How do we solve them? So when we're talking about linearly independent or dependent, we're basically checking if the vectors in our set can be expressed as a linear combination of each other. So what we do is we typically solve this equation. So if our vector has 2 components, or we have 2 vectors with 2 components, it'd be this equation. Remember that in here, we're given what x is. So x1 and x2, those are accounted for, they're good to go. and we know what y is. So y1, y2, also good to go. And at the very right-hand side, we have 0, 0. Easy. The only thing that we don't know in this equation is alpha 1 and alpha 2. So all we're going to do is solve this system of equations to figure out what alpha 1 and alpha 2 are. Now, it was already given to us that our equation is linearly independent. So what should alpha 1 and alpha 2 be if it's linearly independent? What should we get for alpha 1 and alpha 2? 0. Exactly. Thank you. You guys are extremely smart. You're making this really easy. The only way a set of vectors is linearly dependent if all the alpha coefficients are equal to 0. So if I had, let's say, 5 vectors, and I were to ask to prove if they were linearly independent or dependent, and I had 5 alpha coefficients, the only way they're linearly independent is if all 5 of those coefficients are equal to 0. In this case, we have 2 vectors, so we have 2 alpha conditions or coefficients. So in order for this to be linearly independent, both alpha 1 and alpha 2 must equal 0. So we are already given that it's linearly independent, so all you guys are going to have to do is solve this equation and show me that alpha 1 and alpha 2 are equal to 0. Because if one of them, not both of them, but if just even one of them does not equal 0, these vectors are actually called linearly dependent, meaning that they can be expressed as a linear combination of the other one. So hopefully that makes sense for part A. Part B sounds really bad, but it's actually easy. So whenever you guys hear the words unique expansion, look for this on a midterm or a final. What it basically means is we want to take a vector and express it as the linear combination of our basis vectors. That's all we want to do. So if we look at our Cartesian vector notation that we did a lot in Eng 130, we can take a vector, let's say 5, 2, negative 3, and we can now express it as follows, where we have our basis vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, and then we multiply them all by a bunch of coefficients. So this entirety right here, this would be considered the unique expansion. So if we look at our particular set right here, we know what Z1 and Z2 are, and we want to write it as we have Z1 and Z2, and we want to write it as a linear combination of x and y. So we x1, x2, and y1, y2, and all we're going to do in this question is just solve for this alpha and beta. So it should be nice and easy. So what do you guys think? Question 4, is it going to be a problem? Any questions concerning question number 4? Are you guys still nice and happy? I'm hoping still nice and happy. Well, actually, probably not nice and happy because it's almost 6 o'clock. Well, actually, let's put, because you guys are the online students. I know that there's only 5 of us in here, but where is everybody right now? Are you guys in Canada, or some of you guys not in Canada? Anywhere fun? Anywhere warm? Actually, it's still pretty warm here, surprisingly. You guys are still shy? That's okay. You guys will warm up later on. All right, so let's go to question number 5. Now, question number 5 is one of those very unique questions in the sense that it was covered in today's lecture, but today's lecture isn't uploaded for online students, so you guys probably have no idea what this is. So question 5 deals with something called change of basis. And basically what this means is that we can take our coordinate system and we can rotate our coordinate system. Now you guys may be saying, Clayton, I thought we're keeping this course practical. Why would I ever need to change my coordinate system or rotate my coordinate system? Does anyone know of an instance in actual civil mechanics that we needed to rotate things? What do you guys think? You guys ever remember something where we had to rotate things to find different stresses or strains or stuff like that? Inclined planes, Moore's circle, that's what I was looking for. Moore's circle. So nice job, Jason. You guys remember Moore's circle? You guys probably hated it. I've never seen someone who liked Moore's circle. But that's what we're going to get into here. Again, what we're going to be doing later on is simulating stresses and strains within a body. Now, if we think of stresses, we said that the stresses depend on the coordinate system. And if we were to rotate our stresses, Well, sometimes they become higher, sometimes they become lower. Sometimes we induce shear stresses, sometimes we can get rid of shear stresses. So that's why we are learning this right here, because this is going to apply once we start talking about stresses. So hopefully that makes sense. All right. So the question says, let B prime equal E1 prime and E2 prime, which is the new orthonormal basis set that corresponds to a clockwise rotation of our orthogonal basis set B. So basically E1 and E2, those are our original coordinate system. And what we are doing is we're taking this coordinate system and we are rotating it clockwise, and then our basis vectors will now be E1 prime and E2 prime. I got a little animation on the next page to really help you guys see what I'm talking about. Now the question says, if U is equal to 2, -1 in the original basis set, and U prime is equal to 1.67, 1.48 in the new basis set, determine the angle of rotation theta and the transformation matrix Q. So again, this might not make a lot of sense, so let's kind of go into the graphics of it all. Basically, this is our original scenario. This is our basis set B, which is E1 and E2. And in this basis set, we have a vector U, which is 2, -1. So this is kind of our original plane right here, our default system. Now what I'm going to do is I'm going to take E1 and E2, my coordinate system, and I'm going to rotate them. But here's the kind of the trick. I don't want you guys forgetting this. We're just rotating our coordinate system. We're not rotating our vector. So once I rotate it, it's going to look something like this. Now notice that the vector U physically did not change its position. It is the exact same on the right as it is on the left. But since I rotated my coordinate system, the components of U prime are going to change. So is everyone kind of clear on what exactly I did here? Is there any questions about what just happened? I'm trying to explain it as clearly as possible. I'll take the silence as probably pretty good. It'll make more sense once the lecture video is uploaded. So how exactly did we go from this coordinate system to this rotated coordinate system? Well, what happened is we used something called a transformation matrix Q. So if I were to take Q, my transformation matrix, and multiply it by the vector U, I get U prime. It's nice and simple. It's going to be this equation right here. And I forgot to do animations. Can you guys see my mouse on the screen? Hoping so. Yes, perfect. So this is the identity that we're dealing with. We have U prime, which is in the new set, and we can obtain it if we know Q and we know this vector U. So Q right here is going to contain the properties of that rotation. Now, normally I would give you guys Q and I'd give you guys U and ask for U prime. But this is a very funny question in the sense that I give you guys U prime and I give you guys U, and I'm basically asking for the amounts of rotation theta. Now the amounts of rotation is actually going to be captured inside of this Q matrix right here. So what we're going to do is we're going to say, all right, well we can expand it to get this. So this is the definition of Q. We know what's on the left-hand side and we know what's on the right-hand side. The only thing we don't know is what exactly is Q. Now, I think to actually really help show you guys this, let's go over our lecture slides today. Because I guess if you guys haven't seen them yet, why not? Are you guys fine with staying 5 minutes later, hopefully? Sorry, just finding the PowerPoint really quick. Hopefully this will help you guys a lot. So again, we talked about what exactly this is. Oops. From current slide. Oh. Sorry guys, having a bit of a malfunction here. Let's talk about this transformation matrix Q. So in general, the components of this rotation matrix can be the following, where we take EI prime and we dot it with EJ. E prime is our new basis set, and E without the prime is our original basis set. So let's show an example on a 2D counterclockwise rotation. Again, here's my original basis set, and we know E1 is 1, 0, and E2 is 0, 1. I were to take this, I'm going to rotate it counterclockwise, and I get the following, where I got E1 prime, and now I have E2 prime. So if we were to look at this formula, in order to solve for the components of Q, all we need is our basis vectors. E1 and E2, they're good to go. We know exactly what E1 and E2 are. They're 1, 0, and 0, 1. The only thing we're missing is these basis vectors in the new coordinate system, E1 prime and E2 prime. So how exactly do we get those? Well, we use some trigonometry. So if I were to look at my new basis set and I were to draw a vertical line, as so, I just created a right triangle. Now, another thing that we talked about in class today is the idea that these orthonormal basis sets, they always have a length of 1. All right, they always have a length of 1. So this hypotenuse there in that triangle, it's going to have a value of 1. So I'm saying, okay, and I'll put my thing on my screen here. If I know that this length right here, this length right here is 1, I can solve for this x component right here. It's going to be 1, the hypotenuse, multiplied by cosine of theta. And if I wanted the vertical component right here, it's going to be 1 multiplied by sine of theta. So I would get that E1 prime is cosine of theta, sine of theta. So I'm going to ask you guys in the chat really quick, do you guys feel comfortable with how I got E1 prime? Yes? Perfect, perfect. We can do the exact same thing for E2 prime. I'm going to draw a nice horizontal line, and I'm just going to solve my newly created right triangle. First things first, again, we know the hypotenuse here is going to be 1. In an orthonormal basis set, it will always be 1. And then I can just do simple trig. So if I wanted the vertical component of E2, so this component right here, we know it's just going to be 1 times cosine of theta. Nice and simple. Now here's where the trick comes in. And this is going to play a role for you guys as well. If I were to look at the horizontal component, we know that it is going to be 1 times the sine of theta. But notice how now this component is now shifted and it's heading left. So intuitively, we know that it is now negative. So that's the only thing that's going to try and trick you guys. So if we look here, we have that negative sign. So E2 prime is going to be negative sine theta and cosine theta. So are you guys comfortable with E2 prime? Perfect. Yes. Thank you guys for responding. So now that we know E1, E2, as well as E1 prime and E2 prime, we can determine the components of this transformation matrix. If we were to look at component 1, 1, it's going to be E1 prime dotted, so dot product, with E1. So if I look here, E1 is 1, 0, E1 prime is cosine and then sine. Well, cosine times 1 is cosine. Sine times 0 is 0. This is going to be cosine. I can do the exact same thing for 2, 2. So I'm going to go negative sine times 0 plus cosine times 1. I get cosine again. I can do the same thing for the off-diagonal components, and I get sine and negative sine. So if I were to substitute these all into a matrix, I can figure out that my transformation matrix for a counterclockwise rotation is as follows. All right, it's nice and simple. Now here's the trick for you guys when it comes to the assignment. The assignment specifies a clockwise rotation, not a counterclockwise. So if you guys were to follow this exact same procedure, the only difference is now you're rotating clockwise instead of counterclockwise, you guys will get a different transformation matrix. The only difference that you guys should find, though, is instead of this sign being negative, this sign will now become negative. Okay? So when you guys are doing your question in the assignment, don't use this matrix. This is for counterclockwise. You guys are going to want to find the one for clockwise. But the key here is if we look at this, it's only a function of theta. So if we remember the equation, we had u prime, which we know, is equal to q multiplied by u, and we know u. Our only unknown is going to be theta. You guys can solve for what exactly theta is. So how are you guys feeling now about question number 5? Hopefully pretty good. It's going to be the hardest question of the assignment. Good? Wonderful. That's what I like to hear. So we're running out of time, but this last question is easy. So this is, that's not what I want. I want the first PowerPoint. From current slide. Good to go. Question number 6, which is a bonus question. So I talked about it in the in-person seminars, and everyone says that bonus questions should be weighted so that it is technically possible to get, let's say, 120% on an assignment. Do you guys like that? Are you guys all good with that too? The chance to get 120% on these assignments? Yep. All right, perfect. So that's how I'll do it. Now, one thing I also want to kind of specify is for the first 3 or so assignments, there's always a bonus question. So a lot of students think that every assignment has a bonus question, but it's not true. Some assignments do, some assignments don't. A lot of the bonus questions will be focused on these early assignments right here. So question 6 says, consider the orthonormal basis set B, which is 3 vectors, E1, E2, and E3. Now it says if the vectors U, which is 2, 1, -1, and V, which is 1, 3, and 5, are aligned in the directions of E1 and E2, determine the orthonormal basis vectors E1, E2, and E3. So this is something we didn't cover in lecture on the Tuesday lecture. This is something we covered today. And the key here is this, orthonormal basis. Orthonormal basis is actually very simple. It sounds like garbage, but it's actually simple. Orthonormal basis have 2 properties. One is that all of the vectors have to have a norm or a magnitude of 1. So for instance, if I'm looking at U right here, does it have a norm or a magnitude of 1? What do you guys think? No, it doesn't. So what we would have to do to make this a basis vector is we would have to normalize it. We would take the vector U and then divide it by the magnitude of U. And the same thing for this one. So that's going to be the first part. And then the second property of an orthonormal basis is that all of the vectors in that basis are perpendicular to each other. Now, we talked about it a lot in class, as you guys will see, but here's the secret. If vectors are perpendicular to each other, then the dot product between them must equal 0. All right, so the dot product must be equal to 0. So if I were to be given a set of vectors and I wanted to prove if it's an orthonormal basis, I would take the dot product and I would verify it's equal to 0. This is a little bit different though because we're not given what E3 is. So let me ask you guys right now and see if you guys remember Eng 130. If I have 2 vectors and I wanted a third vector that's perpendicular to both of them, what would I do? Do you guys remember? If I wanted a resultant vector that's perpendicular to my 2 input vectors, what would I do? Cross product. Exactly. And that's exactly what we can do. If we take the cross product of 2 vectors, the resultant vector is going to be perpendicular to both. So again, basis vector properties for an orthonormal basis. The vectors must be orthogonal, so the dot product is equal to 0, and the vectors must have a unit norm. So if we were to look at our 2-dimensional vector space and we have E1 and E2, we can actually expand it into E3. All 3 of these basis vectors are perpendicular to each other. So here's what we're going to do in the question. There's going to be basically 2 parts. One is solving for E1 and E2. So the best way I like to do it is I like to draw E1, E2, and E3. All 3 of these vectors right now have a unit norm, and they are all perpendicular to each other. Now the problem says that vectors U and V are aligned with E1 and E2 respectively. So this means that U and V are already perpendicular to each other. The problem that we have though is these vectors don't have a unit norm. So they satisfy the property of being perpendicular, but the only difference is they're not normalized. So in order to get E1 and E2, all we have to do is normalize them. And if I were to draw a picture of what this means, well, currently it means that U is much longer than E1. By normalizing it, I'm basically just shrinking it. And if you guys remember from Eng 130, the idea of taking a vector and dividing it by its magnitude, this is the same as getting the unit vector. All right, so that's all we're doing here. E1 and E2, all we have to do is take our vector and normalize it, nothing else. because it already meets the condition of being perpendicular. Where it starts getting a little bit tricky is figuring out E3. So remember that if we have two vectors and we want to obtain a third orthogonal vector, we use the cross product. As Jason said, it was great. So you guys already know what you're doing. But we have two different options. So at this point, we have four vectors. We have u and v, and we now have e1 and e2. But there's going to be a difference. If I were to cross u and v right now, if I were to cross u and v, would I get e3? What do you guys think? If I were to go u cross v, do I get e3? No, you have to normalize it. See, this is too easy for you guys. You guys are already laughing. And that's exactly it. You will get a vector that is perpendicular, but then you need to normalize it. But remember, we said that we also have e1 and e2. Now, if I were to cross e1 and e2, would I get e3? Yes, exactly. So you guys have two options for e3. First one is cross u and v to obtain a vector w, and then normalize it. Or you guys can cross e1 and e2 to directly obtain e3. Again, if I were to take u cross v, I'm going to get a vector that's in the proper direction, but it's probably going to be a lot longer than the magnitude of it's going to be a lot more than 1. So that's it for the bonus question. So overall for the assignment, how are you guys feeling? Is it pretty good? Not too bad? I'm hoping for it to be easy. Not too bad? Perfect, perfect. Keep morale high. Wonderful. So that is it for today's seminar. Thank you guys for joining. I know it's hard at night, so hopefully I'm not inconveniencing your schedules so much. So that's a good question, Jason. So Jason's asking if we can change it so that the values remain the same on every attempt. So what I'm going to say is we're not going to do that. The reason why is because it was a trade-off. We give you unlimited attempts, but it's at the cost of everything's going to change. And the logic was this, is if you guys can keep getting the correct answer no matter what the numbers are, you guys are learning it very well. Now you guys may be saying, Clayton, well, that's kind of a dick move. I don't like that at all. I don't blame you. But here's the key here. So it sounds bad, but it's actually not bad in the sense that from assignment 2 all the way until the end, we are going to be using Mathematica for everything, which is a software. So when you guys get the questions and you guys finally get the code right, all you guys have to do is just keep switching your input values into your code. You don't have to redo anything else. Does that make sense? Okay, perfect, yeah. It's bad right now, but again, later on, it'll just be switching 3 numbers in your code and you guys will be good to go. And it really helps because I've seen students that accidentally got the correct answer last year, and then they realized once they started a new attempt that they were actually wrong and there was some errors in their code. So again, it's to help you guys be ready for any possible scenario. The assignments, unlimited attempts, they're basically just there for you guys. So yeah. All right, so I will stick around for a little bit, of course, until everyone leaves, actually, basically. So if you guys have any questions, you're welcome to stay. So that's a good question. So there was actually kind of a coding error. I was asking my TAs about this, but apparently question 1, since it's bijective, it's also injective and surjective. But if you were to just check one of them, you get full marks, so it doesn't really matter. What I've seen was it was bijective, a student only selected injective, and it gave them full marks. So it's kind of a coding error. I wouldn't worry too much about question number 1. But if it is bijective, you should tick all 3.